First, I would like to thank the organizer for inviting me. It's very nice. And also I apologize if you have seen some part of the talk already, but it has been, its objective is to be introductory in the context of query problems. So what is the general problem in the background? The general problem in the background is the problematic of query problem. And in databases. So what are these kinds of problems? We are given data. Can you see the pointer? Yes. So usually structures in terms of relational, in this context in terms of relational tables. And on this data we are asking some questions like decision question, is there a teacher for each basic course? Or more complex questions, such as computing aggregates on this data, for example, counting the number of advanced courses here, or more complex, listing the set of solutions to a query. So, how is it related to logic? Well, more or less, a good way to formalize this kind of problems is to use logical formalism as a model for query formulas. And in this talk, we will mainly consider first-order formulas, so first-order queries. So now everyone here is familiar to what is a first-order formula, I guess. And in this talk also, special attention will be given to the positive primitive fragments, also called conjunctive queries. That is, formulas which are not only first order, but that allows only to use existential quantification. Okay. You want to record it, I guess?
Yes.
Yeah. Existential quantification and conjunction. So very basic questions, but which turns out to be very natural and very frequent in database. They are equivalent to select project join for those of you who know SQL. Okay, and I will come back on. I will let you do.
Recording in progress. Okay. Sorry.
It's okay. It's okay. I should have thought about this. Okay, just a common vocabulary. We will call, okay, if we consider, for example, such kind of queries, Z will be the quantified variables. So here are the two alternative forms to talk about the same kind of queries. And X and Y are free variables. So why such a distinction? Why pointing out free variables and quantified variables? Because they will both play a role in the algorithmic problem that we will consider. Since most of the problems that we will consider are non-trivial, so we are expecting an answer which is not simply yes or no. We will have to compute something, and to compute something, we will need the help of quantifier of free variables. Okay, so this is the formula part, so the question part. And for the data, of course, everything will be modelized by first-order structure in a classical sense that we have seen a lot of times since the beginning of the workshop. And in the rest of the talk, I will mention quite a number of complexity results. So, to talk about this complexity result, I need a notion of size, and I need a notion of complexity measures, and I need a notion of models of computation. So just have in mind that the notion of size for the database will be more or less the number of tuples times the size of each basic information. And what is the size of a query? The size of a query is just the list of symbols that is required to write this query. Okay. And also as a model of computation, I will use, okay, I will not enter into the details, but this kind of models of computation corresponds to what you call intuitively algorithm so no Turing machine, but a high-level programming language. Okay, and the objective of this talk will be so to have an overview on 3 basic tasks in database: the task of deciding, the task of aggregating information, and the task of enumerating the result of a query. And with 2 or 3 meta goals, I would say. One is, of course, that the source of tractability and hardness depends on the kind of problem that you consider. Okay. And also, it's very, very nice to, when we look back at this, that most of the complexity measures that are now considered in this area didn't exist before considering this kind of problem. So usually the problem comes with its own notion of tractability, as we will see. So let's have an overview of what are these 3 main different tasks in database. So if I summarize in logical terms what is a query problem, we are given a first order structure, I will call it database, a query with potentially 3 variables. And what usually one tries to compute is the list of tuples that satisfy the query on this data. Okay. So in the Boolean case, when there is no 3 variables, it's just a model checking problem. So we are trying to evaluate if a structure satisfies a formula. The counting problem is nothing else than counting the number of tuples that satisfy. Okay. And usually, because there are multi-parameter problems, there are different ways to measure the complexity of this kind of problems. The first one is called data complexity. So in this context, one supposes that only the structure is given as input and the formula is fixed. Or combined complexity, when we consider that the 2 parts, the data and the formula, are part of the input. And okay, if a way to refine this second one is to look at this in terms of parameterized complexity. I will not do it here. It's just considering the 2, but considering also Q as a parameter. So try to evaluate what is the effect of Q on the complexity. Okay, I don't know how many of you are familiar with complexity class, so because this is a mixed audience. So to summarize, I would say the general problem of evaluating the complexity of a query problem, would the formula be first order or simply existential, is hard, with different level of hardness. So for conjunctive query, it's NP complete, and for first order logic, is P-space complete. So I will not enter more into the details of these classes, but a simplified view of this is that if we try to evaluate a formula against a structure, then the basic complexity of the naive algorithm is always this one. So if we have a formula with k variables, in general, we don't know how to do better than listing all the possible value for the first variable times the possible value for the second one, and so on and so on. Okay. So a natural question is whether one can do better in general. So having this kind of evaluation, but for a fixed polynomial, which would not depend on the size of the query. So it turns out that it's not possible modulo some reasonable complexity hypothesis. And one intuitive way to understand this is that, okay, suppose you are interested by the k-click problem, so you want to know if a graph has a k-click. Then, a natural way to express this as a formula is this kind of formula. And it's hard to imagine, and there are some reasonable algorithmic hypotheses for this, how to evaluate if a graph has a k-click in polynomial time with an exponent that doesn't depend on the size of a click. Okay, so this was for deciding. Okay, these are the Boolean complex class for the Boolean complex problem. What about enumeration? So this time the objective is to, for enumeration problem, is to generate one by one all the results of the query. And of course, if you consider a formula and a database, the number of solutions, so the number of tuples, may be larger than the size of the database that you have at the origin. So a good way to measure the tractability of the process is not to consider everything in terms of the output size, but to measure the dynamic, as a dynamical system of the processes of enumeration. And I will, and while, for example, in the context of decision problem, we consider, polynomial time as a central class of feasible problem. Feasible. For enumeration, the tractability can have different forms. And they are, I would say, classified in three main, there are three main ways of talking about tractability. The first one is to consider that we have an algorithm to solve a problem which at the end computes everything in times which is polynomial in the input size and the output size. So this is some kind of, we know that it will work, but we don't know how. Okay. A bit better is to have incremental polynomial time. So this time it corresponds to a situation where we have an algorithm that to compute the I+1 solution takes a time which is polynomial in the input size and I. So this is a kind of snowball algorithm. So you have something that is getting more and more complicated as time is running. And the kind of graal of this measure is a polynomial delay. So this time such an algorithm works in such a way that we are able to enumerate all solutions of the problem with only with a guarantee that between two solutions there is a polynomial time in the input size between two solutions. Okay, but this is not good for database in general and for logic in particular, because in the database context, spending a polynomial in a database amount of time to generate the next tuple is far too expensive. And people started to concentrate on another notion of tractability, which will depend only with a delay which will depend only on the tuple size. So something that we will see is called constant delay, that allows to enumerate tuples one by one with a guarantee between the delay, with the guarantee in the delay between two successive tuples, but a delay which would be very, very, very small. And
to make sure that you understand as well. So this is like you want polynomial time, but to allow an extra parameter, which is the time, the number of steps.
Yes. So maybe it's better summarized here. So for this kind of enumeration problem, we will divide the algorithm in two parts. One would be the pre-computation. So a necessary amount of time to build a data structure, which would be as small as possible. And when it is done, when this pre-processing is done, the enumeration starts, and the delay that we will impose, and we will call this class, call this class constant delay, will be that the delay between two solutions will be more or less proportional in the size of the formula only. So we forget the data, and only the formula is a reference between. Okay. So is it natural? So are there examples of this in the nature, I would say? Okay, if the query is simply this, so this means that we have a database which is a graph, and we want to enumerate all edges. of course it's trivial, so we can arrange a data structure and list the first edges, the second one, and so on. If we have this, how do we proceed if we want to have a constant delay algorithm? So basically, we will take the two relations, R and S. Because we have a common variable, we will sort the two relations in this second, according to the value of these second variables. So we will have this and this. And now what do we do? So we run concurrently into the two relations. And each time we have a correspondence, we enumerate things. And since they are well sorted, it will be a constant delay process. So we will have no time to wait. I mean, we will not have to wait so much between two tuples. Okay, so what is the situation of this? So in this one, so here we wanted to have the three variables as an output. So we enumerate x, z, and y. Here we forget the z. So this means that we want a constant. So this means that, for example, for A2 and for A and 3, there are two possible values for z. No. Okay. So this means that if we want, for example, A and 3 and B and 4, we want to enumerate it once, okay, without repetition. So we have to find a way to skip all the redundant values. Okay. So is it possible in constant delay in general? Okay. So if you look at this and consider that R and S are a relation representing n times n Boolean matrices, what this query is saying is that we want to have the multiplication, the result of the multiplication of two matrices in the Boolean case. Okay. So imagine that the result can be enumerated in constant delay after, say, a linear preprocessing. So this means that we will be able to enumerate all the coefficients of the result of the multiplication of two matrices, okay, one by one, with a constant delay between each. So in total, what does it give as a complexity bound? It means there is at most n square values. N squares times the constant is n square. Okay. Linear preprocessing will mean that it's still n square, and we would have solved the Boolean multiplication problem in n square. So, which is globally unexpected. Okay. So what does it mean? It means that modulo some algorithmic hypothesis, this kind of simple query cannot be enumerated. Yes. So now I arrive to the objective of my talk. It's to consider two kinds of context in which we will talk about complexity of query problems. One is, so we have seen that in general everything is hard. So there are two ways to find tractability, either to restrict the data or to restrict the formulas. So we will have a quick tour on each of these possibilities. And first, to consider restricting the data and exemplify the role of sparsity. And second, to restrict the query, but on arbitrary data, and then exemplify the role of high cyclicity, hypergraph decomposition, and the role of free variables. Okay, so I will probably skip some part at some point. So, same problem, FO query are hard. We want to find cases where we can for sure guarantee that we will answer to a query in a polynomial that depends only on some constant and not on the formula. And it turns out that if we don't want to restrict the query, so if we want to be full first order, then we need to restrict drastically the size, drastically the properties of the data, and here it's where sparsity comes into the play. So I will take a very simple example. So sparsity 101, I would say, which is a bounded degree. So the smallest class of sparse graph that you can imagine is the class of bounded degree. So you fix the degree, you have an infinite class of graphs, and you know that all the class of the graph of your class have a degree bounded by say 3, for example. And now we are in first order logic, and we have data which is ultra restricted, I would say, and we will play with two main ingredients with these two main ingredients. First, playing with the fact that first order queries are local, so which means that a first order formula can talk only about its neighbors, more or less. So it depends on how rich is his neighborhood. And second, that bounded degree graph force that each vertex in a graph has a constant number of neighbors. Okay, so how do we proceed for this? So, no, what were first the early results known about this? Playing with game technique, Hennenfent Freiseg game techniques, Caesar in 1996 proved that, okay, no matter the number of variables you have in this formula, it's possible to test whether a structure satisfies the formula in a times which is basically linear. Okay, so this was the first result in this area. So I mean, considering bounded degree relation. And if we use Caesar's result and a naive branch and bound technique, okay, we can arrive to a total time algorithm which will be in this. So fix one possible candidate and test it. It turns out, in fact, that maybe there is room to do a better job and to replace this multiplication by an addition. So having something whose complexity would depend linearly on each of the parts. And to do this, so this is an ultra simplified view of the problem, but it's on very simple example, so you can cheat a bit. A method of proof that appears to be very efficient is quantifier elimination. So quantifier elimination, most of you are logicians, so for you it has a different meaning, I would say, that what I will explain, but in the spirit it's the same. So what is the objective? Is we start with a formula, it has k variables, and we have also a structure which is of bounded degree here, which is quite sparse. And the objective is to eliminate one by one these quantified variables to the price of an additional computation on the structure. So you are allowed to enrich a bit the structure, and so that you can decrease somehow the complexity of the formula. So in particular, this means that finding another formula with one variable less, doing a bit of computation on the database, and hoping that the result of this new formula on this new database will be the same as the result on the old formula on the old database. Okay. As I said, it's ultra simplified, but somehow for all the results that followed, it's the kind of trick that is used, although it's not explicit for the formula part. Okay, so in our 101 example, how do we do? So usually if you want to eliminate variable, it's better to have a functional context than a relational one. So it's easy to reformulate the bounded degree case in terms of a formula about functions, about injective functions. And if you want to eliminate variables, okay, the basic is to be able to find a solution to eliminate one variable in a context where it is existentially quantified. And then, yes?
What is a vocabulary of injective functions?
So you have functions, and you have a semantical condition that says that you cannot have two.
Okay, so there's like an axiom.
Yeah. Okay, so we have a formula like this. How do we proceed to eliminate y? The basic things that we can do is to check how many values satisfy psi, and check if there are enough that avoid this. Okay. Yes, yes. So it's having a big bags, the psi, and then trying to find one element in these big bags that avoid all the functions. Okay, this is a constant amount of information, more or less, modulo the fact that you are able to evaluate this. And I will not enter more into the details, but this can be plugged into the formula. So modifying the formula a lot, so that we have at the end a new database that have additional information on how many values satisfy this, and one variable less. Okay, so if for this example, it's really easy to build a concrete elimination procedure, but the size of the formula will be like this. And once we have done this, it means that we have no quantified variable anymore. So we have a quantifier-free formula. And is it easy to enumerate the result of a quantifier-free formula? Well, okay, so you have a formula like this, psi, additional free variables here, and the same kind of constraint that we have before. What do? We enumerate all possible value here times all possible value here minus those, the constant number of those that will make this fail. Okay. So this means that we have an enumeration procedure which more or less enumerates the result of a Cartesian product with some holes, but with a constant number of holes that you can evaluate. So this will be constant delay, for sure. Okay, I hope you believe me. This can be formalized a bit more, and I mean, a series of results in 15 years ago showed that more or less, if you are interested by counting, outputting the number of solutions, deciding enumerating, and so on, more or less everything is linear in the size of a database, and it's possible also to evaluate the size of a constant. So the constant associated to the delay is 2 to the 2 to the 2 to the O of k. So. Okay, so this was the first basic example of a series of a huge series of works on this subject, which are maybe more exemplified here. And I am happy that some of the main actors about this part and the part that will follow are in the audience. So we have looked at this, okay, bounded degree. So there is of course another starting point that is possible, which is bounded tree width. And all of this is some kind of ladder of more and more evolved notion of sparsity. That leads to a boundary here where the complexity jumped from easy to hard in one step. Okay. So we will maybe just have a look at this a few minutes, and before moving to a different context. So for this, I don't know if you managed to read it, but here we have a class that is called nowhere dance, and here we have a class that is called somewhere dance. Okay. So nowhere dance is a notion that, okay, for this I need to step back a bit and define what is a R minor. So we have a graph, and we say that another graph is a R minor if it's for R being a constant, if its vertex set is a subset of, can be seen as a subset of vertices of the first graph, and if we can group the original vertex set into bags of R radius around some point, and look at the graph that is obtained once we consider all of these bags, which are supposed to be disjoint, as a unique vertex. And a graph is nowhere dense if somehow for each time we fix a constant, there is some other constant nr such that the clique of size nr is not a minor of a vertex of a graph of its class. Okay, so it turns out that it's a very rich class of structure, and what is really beautiful is that it has many equivalent definitions. I mean, it's really amazing for me. And so what are the positive results? So I'm not sure I have cited everyone, but okay, if you are interested by the same problem as before, deciding counting or enumerating, then there is a tractability result, except that the linear phase is now 1 plus epsilon for every epsilon. What about the other direction? We'll say that a graph is somewhere dense if it's not nowhere dense. So it's a very basic definition once you understand the first one. And it turns out that I think it was with another notion of somewhere density which has been proved to be equivalent after, no? That Dauer and Kreutzer proved that the model checking problem over nowhere dense classes of graph cannot be easy. So don't try to read the name of a class. It cannot be easy. I mean, it cannot be as before. Okay. So this means that for classes closed under substructure, the frontier between tractability and intractability is the nowhere dense, somewhere dense frontier. So here. Yeah. So is it the end of the story? Well, if you look at the classes that we have considered, they are all closed under substructure. So if you are of bounded degree and you take a substructure of a graph of bounded degree, you're still of bounded degree, and so on for, I mean, also for nowhere density, bounded expansion, and so on. So what would be the situation for classes of graph which are not closed under substructure? And again, one very basic example is this one. So consider a class of graph which are made of a clique for each k. The graph is made of a clique of size k, and then a huge number of isolated vertices. Okay. So this is not a class which is closed under substructure, because if you eliminate all the so we are considering the class of graph of degree O of log n. Okay. So for this, we take a small clique and a large number of isolated vertices. So if you eliminate the isolated vertices, then the graph that you obtain is not O of log n bounded in terms of degree. But anyway, I mean, it can be proved that also, as for the case of nowhere dense graph, for this kind of graph, there is tractability result that shows that deciding, counting, and enumerating can be done easily. Okay. So this means that although the classification for classes closed under substructure is done, there is a lot of work to do, and which is now being to be done on more general classes of graph. So I will stop here for this part. So it is clear that now there are investigations for more general classes of graph, which is underway, considering that the case of the classes of structure closed under substructure is totally solved, and it's now nice to see that I mean this kind of study is now meeting widely studied model theoretic notions such as stability or NIP classes and so on. And okay, I will stop this on here. But so as I said, I am happy that a lot of main actors of this new direction of research are now in the audience. So if you have more precise questions on this part of the continuation of research, then they will answer to this better than I. Okay, so this was for letting the query as it is and impose restriction on the data. So now we will let the data as it is and impose restriction on the query. Okay, and of course, same objective. So we know that everything is hard. We know that we are looking for cases where we can have better bounds. We know that we don't want to restrict the structure, so we will look for restriction on the formulas that will allow to have a better result in terms of enumeration. And if possible, this is maybe a more realistic point, axe of research for database theorists. If possible, consider kind of query which are really used in practice. And it turns out that in this context, yes, acyclicity, hypergraph properties of free variables, I mean topological properties of the free variables will play, is playing a big role. Okay, so now we will stop considering first order query as a whole. We will focus on the primitive positive part, so we are allowed to use only conjunction and only existential quantification. And maybe something which is not familiar, I mean, vocabulary which is not familiar to logicians. Database theorists distinguish usually two kinds of queries. Those which are called self-join, so which allow reusing the same relation twice, or self-join free, so which forces to use database relations which are different each time. Okay. So we start from a formula, which is existential and conjunction. And a good way to look at restriction on this formula is to associate to this formula a kind of structure, could be a graph, an hypergraph, and so on, and look at the restriction on this hypergraph. So we will choose to associate an hypergraph to this to a query. So how do we do? Here is a query. And the hypergraph will be the structure whose vertex set is the variable set of the formula, and whose hyperedges, this is the name of the edges, are the atoms of the formula. Okay. And a central notion in this area is that of join tree of an hypergraph. So it's a tree whose nodes are hyperedges, and which has this same kind of property as for bounded tree width, meaning that each time we'll consider a vertex, the subtree in which this vertex appears must be connected. Okay. So it's like bounded tree width, except that you have only one hyperedge on each pack. Okay, so what can we do for, and we will say that a query or a formula is acyclic if its hypergraph can be decomposed into a tree like this. So this is strange. This doesn't seem to be acyclic. But it is. So there is a way to, I mean, this is a tree. It corresponds to this, and it satisfies the connectivity property. So this is something which is acyclic. So acyclicity notion in hypergraph are not all, I mean, there are various notions of acyclicity in hypergraph, and there does not always corresponds to what you think is acyclic in graph. Okay, so a very, very old result and very famous is due to Yanakakis, that says that if you consider acyclic queries, and if you want to, I mean, decide if it's true or not, or if you want to compute the result set, then you can do it in times which is linear, but with a multiplicative factor in terms of the size of the formula, the size, linear in the size of the formula, linear size of the database, and linear in the size of the output. I will not show how this algorithm works, but okay, believe me, usually when you have a tree, it's a good sign, and you can do everything bottom up, and if you want to compute the result bottom up, top down, bottom up, such that you compute everything in linear time. And of course, this kind of result can be turned into an enumeration algorithm that intrinsically requires a delay between two tuples, which is linear, but linear in the database.
What is this phi d here?
So it's the result of it's the set of tuples that satisfies the query phi on the database D.
Ah, okay.
This is, Yes. So which can be, I mean, among these three objects, this can be the bigger one. I mean, it's easy to compute something that will be really, really far bigger than this and this, especially if phi is part of the input. Okay, so here the question is it possible in this context also to talk about constant delay? So to have efficient algorithm for natural class of queries that allow for a constant delay.
Sorry,
yeah?
can we look at it again? We are computing the set phi d here.
Yes.
And we use in time, and here we use it. It's
yes.
size.
So it's a retrospect.
We use the size when we haven't computed it.
So it's when you look back at the process, you know that there is the algorithm always works in time, which is
okay.
like this.
Okay.
But you're right. I mean, it's ugly, but it's strange. Yeah. Yeah. Okay. So the objective is to find a query which are easily enumerable. So let's start. So we have seen that this is easy. This was the first example. This is the same query, but without the z. We have seen that it seems to be hard because it's equivalent to Boolean matrix multiplication. This one. This one. So what is the difference between this one and this one? I think this is the place of the variable here, which was before here, and this one was here. So x1, x3 has been permuted. Okay. This looks like a complicated query in both cases, but this one is easy and this one is hard. And so we'll try to see why. So on top of acyclicity, we will add an extra layer of acyclicity in the following way. So let's start with the formula phi of x. So x are the set of free variables. And we decide to add a new atom to the data, a new atom made only of the free variables, okay, which is here. And then look at the query that we obtain. And check if it is acyclic or not acyclic. And we will say that the query is free connex in case this is acyclic. Okay. So we start with this one. It has two free variables, x and y. So I add an atom which contains x and y. Blah, blah, blah. Where is it? Here. Okay. And now I look at, is this acyclic? Okay, xw, yz, z alone, xy, there is a path, it should be acyclic. Okay. Consider the formula for the matrix multiplication. So we have xz and zy. We have also xy as free variables. So we add an atom with xy. What do we have? xz, zy, xy. It's a triangle. It's not acyclic. Okay. Okay. So this is the notion of free connexity, and this notion of free connexity can be also considered in a slightly different way. I mean, seemingly different way because it's equivalent. So let's consider an acyclic query as a starting point with x as a free variables. Let's consider its joint tree like this. And now we will check if it is possible to add new atoms, but new atoms which are subset of the original atoms, such that these new atoms contains only free variables, and such that at the end we have a connected subtree that contains only free variables. So for example here I can add a new atom x2, x3 that is a subatom of this. So in terms of data, this is safe. Somehow I have a huge data and I take a projection of it. And we add it at the right place in a tree. And now we have three x1, x2, x3 free variables. We have managed to isolate a part in the tree which is connected and contains all the free variables. This makes the query free connex. This is an alternative way to show, to see free connexity. So for free connexity, we have two ways. Either we add a whole atom containing the free variable and check for acyclicity, or we have this seemingly less nice way of checking free connexity, but which will be better in terms of algorithmic content. Okay, so we have a free connex query. Now the question is, how can we be sure that each time we have a free connex query, we are able to enumerate with constant delay? So this is really simple. So let's summarize. We have a database with free connex acyclic conjunctive query, and we want to enumerate the set of data in times which is linear, with a linear preprocessing and constant delay between each tuples. So it's very easy. It's made by filtering, I would say. So it's very classical algorithm. We start from this. Now what we will do is to kill these atoms one by one by filtering. So the first step that we can do is to filter T against S. So doing this, we want to update S and keep in S only the tuples A, B, C, such that A, B, C of course belongs in S at the beginning, but that there exists D and E such that T, S, D, E, so that S, D, E belongs to T. So because we have Y3 that appears here and here, so we want to find, we want to filter, we want to eliminate what is not interesting here. Just keep what would be relevant at the end to evaluate the query. So do you believe me? That, okay. So let's do it. Okay, so at the end we have this. And now what do? Now we have a subquery which is connected, which has no quantified variables. And we are back to the first example that I have given in the talk. So we can enumerate everything one by one. Okay, so this is what we have done in the first example. Okay, last thing. So we know now that everything that is free connex is easy. What happens to what is not free connex? And we can show that it is hard by reducing every such query which are not free connex to the Boolean matrix multiplication. So how do we do? So the generic tool is this one. So we have this query for the Boolean matrix multiplication. And we also have a non-free connex formula phi that we have to evaluate, whose complexity we have to evaluate. And what do? Starting from the database for the Boolean matrix multiplication, so starting from the two matrices and starting from this query, we built a new database. For each time we have a query like this, we are able to build a new database in time which is linear in the matrices, such that the results are the same. So if we are able to do this each time we have the free connex queries, it means that there could be no efficient algorithm, there could be no constant delay algorithm for any free connex query unless we have something unexpected happening for Boolean matrix multiplication. So last technical thing. How do we proceed? So suppose we have this formula which is not free connex. We have our original matrices A and B and this Boolean matrix multiplication product. What do we have to do is to exhibit witnesses of non-free connexity somewhere. And then from A and B build relevant data for E, S, and T, like this, such that both queries are the same. So that the evaluation of this over this is will give exactly the same result as the evaluation of this over this, up to isomorphism. Okay. So to summarize, this gives the following general, very basic example. that if you assume that the matrix multiplication hypothesis, so that no square matrices in m times n can be computed in n square, the multiplication can be computed in n square, then the situation is really simple. If you have a conjunctive query, either it is free connex, and then you can enumerate in constant delay, or it's not free connex, and then you cannot. Okay, so this was also a 101 example of in result in this area. There have been a lot of further research in this context. If we want to count the number of solutions, then we have to follow a path which at the beginning looks like similar to what we have done so far, but where we have to elaborate far more complex models of how the free variables are spread in a formula to measure when counting is tractable. Again, as often in graph theory, the star is a problem here. So if you have a star, you have a problem, and so you have to design measure of spreadness that of free variables that would make you far from being a star. And okay, and so I could also have mentioned works on union of conjunctive queries, where something very nice happens is that you can have hardness starting from two easy cases. So you have two easy queries, you want to enumerate them, but unfortunately, if you want to enumerate the union, it's hard. So you have again to have to devise a new notion based on I would say hypergraph properties. Okay, so this was a very quick, maybe a bit too dense illustration of the role of logical and combinatorial method in the complexity of various tasks in database. I mean, subject what we could have explored, but what we have not done here, and that come with their own set of combinatorial methods each time. Are the following. Suppose you want to have queries with higher order free variables. So you have first order query, but you have higher order free variables. And then now what is important is, I would say, alternation of quantifiers. And the main central notion that appears is more approximation of enumeration than enumeration itself. If you can be interested in practice, it's the case by a cyclic conjunctive query where you have in the background some linear ordering and so on. And then, I mean, to solve things, you can use combinatorial method like color coding problems or color coding algorithm and so on. And also considering ACQ with negation, and then you enter directly in the world of SAT and CSP. Okay. Also, one very active field of research also is to consider this kind of problem where the data can change during the process. So you have the data that you want to enumerate, but your data can change. So also again, this is an area where there is a lot of things to do for a logician. And also one thing that I have not explored here is why not, instead of algorithm, considering that this is formula which are the enumerator. So you and consider enumeration by formulas or small depth circuits with retroaction. So you have imagine you have these things. So imagine that here you have a formula. So you have a structure. You give this structure to a formula. It computes something which will be your next advice to compute something else. So you have a circuit with retroaction here, and you want to compute the solution of a problem. Why considering this? One, because it corresponds to a lot of enumeration procedure. I mean, there is a lot of even when these things is restricted, this corresponds to a lot of enumeration procedure. And two, it's for the first time it gives a framework which seems to be nice to prove lower bound, which is a regular problem in terms of complexity in general. Okay, so that's all. 57. Yes, thank you.
Other questions?
Tu veux ça?
Thank you very much. This was such a really interesting talk. This doesn't work. Okay, so thank you very much. I find this talk very rich, interesting. Many questions and queries for you. But I was just thinking about the first part of this idea where you are allowed to do something with the data when you keep the query. So if somebody gave me a problem like that, I have this huge graph, and now I am in a nice case, which I will think about like stable. So this nowhere dense, I will think in terms of stable graphs. Now I know if I have a stable graph, the similarity theorem applies without any exceptional pairs. So I can split this stable graph into into a number of smaller pieces, all of the same size, and each one is regular. So now, with the high probability, my query can be approximated by queries on this. I'm sure people have thought of this before. So I just wondered what this gives actually.
I'm sure I'm not the best person in the audience to answer to this kind of question. I know. I mean,
just can you combine with probability? That's if you want just to simplify the question to this. You want an answer, but it's only not completely sure, but it is with some high probability.
So, as for me, in this context, I have not considered it. It was, I mean, with Jan Strozicki, we have done it, but in a slightly different context, where the reason why you can use probability doesn't come from the data, but from the formula, and then you can have approximation of, in particular, the number of solutions. So you can have, I mean, a randomized approximation of the number of solutions. But for your specific question, maybe Michał or Patrice have an answer.
Maybe not an answer, but some comment. So the first point is that about the regularity lemma for stable structures. Okay, it should be about structures and not simply binary structures, like was originally in Manière-Scheller. So this is the first point. Second point is there is a computational problem of computing really the partition, which is, okay, you don't have exceptional pairs, but they are not homogeneous. They are excellent, so to say, but it still you have some work to do on these things to extract the information. It's not completely clear how to do it. And finally, about probabilities, the problem is that when you simply check existence of one solution, globally it can be almost zero probability. It could be some stupid thing that will completely disappear in the decomposition, because it will be in this small garbage that you have there and there within the pairs, not homogeneous. Okay.
Are there other questions or comments? Please.
Okay.
Maybe I will also comment on this question of Mirna.
Yeah.
There was a work, I think 2 years ago, by Dreyer and Rosmanif, who were considering extension of FO by kind of counting quantifiers, saying that there exist that many variables, evaluations of X that satisfy something, up to some epsilon approximation. So it's like an approximate FO. And they were, I think, doing model checking on classes that are have bounded expansion. I don't exactly remember if they did enumeration as well, but probably it goes in this direction that you are now pointing to. The reason why they are able to do it because we have a lot of very strong structural tools for bounded expansion, and as Patrice mentioned, regularity lemmas for stable classes, and the fact that we are not really able to compute those kind of decompositions are still a problem to extend this kind of results in this direction.
Other comments or questions?
Sorry.
Okay, so let's thank Arnaud again.